Hi everybody, Augie Kennedy here again with super awesome calculus. And we're still on chapter 6, integral applications of integrals. And today we're going to go over another way of computing volumes. Last time we talked about the volumes by taking cross sections of circles basically, and figuring out that volume is really just the integral of the area. Well, today we're going to learn a new way to do volumes that will help us evaluate some functions that otherwise would have been very hard or impossible to do. But first, let's go over the question that I had left you with last time. Last time I asked you to find the volume of the solid. X equals y squared, and x equals 1 around x equals 1. So this is pretty easy to set up. We know what it's going to look like. We're going to have y squared, and we're going to have 1, and we're going to rotate it around x equals 1. So we're going to get something that looks kind of like some sort of football. There we go. Well, that's not a very good looking football, but that's basically the type of shape that we're going to be looking for. Now, in this case, what we need, the key observation to make here is, first of all, that we're flipping around x equals 1. We're not flipping around x equals 0. Now we know that the area, we could go ahead and we could take cross sections, but then we'd have y squared, and we don't necessarily want to solve this in terms of square root of x. That might be a little bit of a challenge. So instead we're going to take these top slices here. And when we take top slices around this, we're going to take, around y, we're going to take something that's basically a dy integral. So instead of taking this with respect to x, we're going to make it respect to y. So it's going to be y. And what is y? Y is, well, hold on a second. Here we go. If ay equals pi r squared, and we've got dy, we've got r equals y squared, well, let's just go ahead and use y squared. Let's not use plus or minus square root of x. So, sorry, that was poorly articulated, but I hope you get the general idea. Not necessarily graphically, but just algebraically, it's a lot easier to just go ahead and solve this with respect to y squared. Y squared squared. And the way that this is going to work is that we don't, well, hold on. R equals y squared squared, right? Well, not quite. Because remember here, the radius of this thing isn't necessarily y squared, because we're not rotating around the y-axis, which is x equals 0. We're rotating around x equals 1. So what we really have is 1 minus y squared, because whatever this value, this height value is, it's going to be not the value of y squared, it's going to be 1 minus that, because we're already out farther, we need to get back. So we have 1 minus x squared, or y squared, equals r. So we square that. And what that means is that via polynomial expansion here, we're going to get our volume between -1 and 1, because these are the y values, ay dy, v equals -1 to 1 of y to the 4th minus 2y squared plus 1 with pi on the outside, dy. And we can integrate this very easily, and we get pi times y to the 5th over 5 minus 2y cubed over 3 plus y evaluated between 1 and negative 1. And when we plug these in, we get pi times 2 plus 2/5 minus 4/3 using the fundamental theorem of calculus. And therefore v equals 16 pi 15ths. Okay. So that's the volume of that area. Or that's the volume of that interval rotated around x equals 1. Now, we're going to talk about volumes by cylinders, cylindrical shells. This is kind of tricky-ish to understand, but bear with me if you can. First of all, we know the volume of a cylinder. Here's a cylinder. We did this before, I believe, in optimization. We discovered that the volume is just 2 pi RH d delta r. All right? So it's 2 pi r, circumference of a circle, times the height of the cylinder. It's a circle, 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 circle. Kind of looks like a dance move. Anyway, that was embarrassing. So, why do we need to know this? Well, let's say we have this curve right here. Let's look at this. We got woo woo. I mean, that's going to kind of suck. Because if we know that this is like y equals 2x squared minus x cubed, we don't know what the hell the values are going to be here or here. We sure as hell don't know what they'd be like there, so we're not going to bother using rectangles. Instead, we're going to take spheres, especially if we rotate this, and we're going to get this, and it's going to be like a whole big tube thing. Well, the easiest way to do that is to make cylinders. We have a cylinder, for example, right here. And then we can have a cylinder right here. And we can just basically take cylinder shells, kind of like rectangles, but because we're going around a surface of revolution, we have a cylinder. And we have rectangle type things, and we know the volume of a cylinder. So basically, taking the volume this way will enable us to take an infinite series of cylinders, find the cross section of the cylinder, and then just take the volume. So, as you might suspect, when we had a cross section that was a circle, we had the integral of pi r squared dx or dy. Here, if we're using cylinder shells, we have the volume is equal to a to b of 2 pi x f of x dx. This is very important. That f of x dx, very, very important. Don't forget about this little x there. So what that means is that basically v equals 2 pi times a to b x f of x dx. It's as simple as that. All you need to do is remember to stick that x in front of the function and you'll be good. Sometimes, I'm just going to let you know, sometimes what you'll want to do, if you're doing a cylinder top down like this, you'll be replacing the x with y. That can happen. You can have a dy integral through cylindrical shells. But what cylindrical shells enable us to do is it enables us to take integrals of things that we used to need to use a dy spherical integral, like the last question, and it allows us to take a cylindrical shell that will hopefully be easier. Let's do a good example of this. Let's find the volume of this solid. Y equals 2x squared minus x cubed, and y equals 0. And we're going to be flipping it around the axis, the y-axis. So, we're going to get 2 equals x squared minus x cubed. We're going to flip it around to y. Here's y equals 0. Here's y-axis, also known as x equals 0. We flip it, and we're going to get some kind of cylinder here. If you were to look down, it would look like a bowl that got slowly steeper. It got steeper as it went down. So the way that we're going to solve this is the first thing we're going to do is we're going to need to figure out what type of range we're looking at here. Well, the range we're going to be looking at, if you plug in the numbers, you'll find that this runs out, y equals 0, is going to happen at 2. 2 squared is 4, times 2 is 8, minus 2 cubed is 8. 8 minus 8 is 0. That's where it's going to intersect y equals 0. And right here, we see that it's 0 at 0. So 0 and 2 are our integration variable, or our integration bounds. So let's go ahead and write the integral. No, I do realize that we go from -2 to 0 and then 0 to 2, but we don't need to worry about that part. We don't need to worry about the -2 to 0. That's taken care of in the formula. The 2 pi, that's going to help take care of the negative part that's created by spinning. So volume equals from 0 to 2 pi x times f of x. Well, f of x was just x 2x squared minus x cubed. And x is the variable we're using, so it's dx. Great. Now, v equals 2 pi, 0 to 2. But let's go a step further. Let's distribute this x through the parentheses. Let's go ahead and do that. And we get 2x cubed minus x to the 4th dx. And once again, we have a very easy integral. 2 at 2 pi times 2x to the 4th over 4, which is actually going to be x to the 4th over 2, minus x to the 5th over 5 between 0 and 2. We know that 0 plugged in is going to equal 0, so we're just concerned with what it is at 2. 2 to the 4th is 16, over 2 is 8, minus 2 to the 5th is 32, over 5, times 2 pi, and we get 16 fifths pi. And that's it. That's all we needed to do. A lot of people, when they tackle problems like this, they get really hung up on the geometry. Now, the geometry is useful insofar as it's going to tell you, am I looking at pieces of a circle? Should I be looking at cylindrical shells? What should I be looking for? That's where the geometry is useful. Outside of that, don't really worry about it. It's just the formulas. And the formulas, I mean, we've only covered 3 formulas so far in this chapter. We've talked about the difference. If you've got an area between curves, that's just going to be absolute value f of x minus g of x, and that integral from a to b. If we want to figure out the volume of something between a and b, and we can use circular cross sections, well, that's just pi r, or f of x, squared dx. And here, v equals a to b, 2 pi r x f of x dx. So those are the formulas. Pick one, whichever one is easiest, use that. And if you can't use x for any reason, well, go ahead and use y. It doesn't matter. Now, for one more example of this, so you can see it in action, because I think that's the best way to see it. Let's say I asked you to use cylindrical shells to find the volume obtained by rotating around the x-axis the region under the curve y equals square root of x from 0 to 1. Alright, well, y equals square root of x looks like that. And we flip it around the x-axis. There we go. We've solved this integral before. We know from the last lecture already that this volume is going to equal pi over 2. It's going to equal pi over 2. But we want to use cylindrical shells this time. So let's go ahead and let's do that. Let's realize that a cylindrical shell, if the curve looks like this, it looks like a bowl out that way, we're going to use shells that go that way as well. And indeed, these are going to be dy shells. So we're going to use y. Now the way that we do this is we need to realize that y equals square root of x, and x, therefore, is y squared. We know that because if we're looking at dy, we want y to be the variable of integration. We can't have x dy. I mean, you can, but that's a different class. We want the y and the dy to both be together. And we can have that because y equals square root of x is just the same as y squared equals x. Same thing. So, let's look at the radius of these shells. Well, we have, let's go back to the original graph right here. Here's the graph we're working with. Here's a shell. Alright? Now what we want to do is we want to find what the radius is. And the radius is going to be y. Alright, so it's going to be y squared. But there's going to be a height issue here. And the height is going to be 1. So basically, 1. So we're going to want, between 0 and 1, that would make the height 1. That means the radius here is 1 minus y squared. Now, let's look at this in terms of an integral. We're going to have the volume from 0 to 1, stated before. Alright, 0 to 1, 2 pi, instead of 2 pi x, 2 pi y. Alright, f of y is going to be 1 minus y squared dy. Pretty easy. Pretty easy. We can solve this very quickly. 2 pi, 0 to 1, distribute the y through, y minus y cubed dy. b equals 2 pi times y squared over 2 minus y to the 4th over 4. Between 0 and 1, we know 0 isn't going to equal anything, so we just look at the 1. We have v equals 2 pi times a half minus a 4th, which is going to give us pi over 2. Ta-da! So using cylindrical shells wasn't so bad once we realized what the height of the shell was. That's where you need to be careful with 1 minus something or 2 minus something. You need to realize that you need to look at the height, not just necessarily as the value, but what the value is subtracted by a bound. You know, if we've got 1 is the edge of the shell, well, the radius of that, the thickness of that shell is going to be 1 minus the value of y, so it's going to be 1 minus y squared. To illustrate this a little bit better, we have the shell, we have the function right here. 1, 1. Let's look at this shell, this big fat shell right here. Do you see how fat this shell is? it's, boom. God dang it, I can't draw right. All right, this is a fat shell. Here's where the first part intersects, right at f of y, and here's 1. So this space in here is 1 minus that, which is y squared. I hope you understand that that's what the shell thickness is. So that's the idea of volumes by cylindrical shells. It's not that hard, and it can be useful. Now, today I have another question for you. It's one of the last questions that we're going to have. So here we go. There's only one more course after the lecture after this, and it's the average value of a function, and then I'm going to give you a quick test. So the average value of a function is next, but for right now, I'd like you to use cylindrical shells to find this. Find the region, the area of this region, between these four parameters. Y equals x cubed, y equals 0, and x equals 1. And I want you to flip all of that around y equals 1. And if you can do that, you're good as gold. All right, well, I hope you had a good time, and next time we're going to do the average value of a function, which will be the last actual lecture. And I really appreciate you watching, and take care. I'll see you next time.